Hi, welcome to Chapter 14, Chemical Kinetics Overview Part 5. This is the last video of this chapter. We're going to be covering Section 14.6, Reaction Mechanisms and Catalysts. So law versus theory. So kinetics is what happens. And how do we describe it? Well, we take some data and then from the data we determine our rate law. Okay. Why do we have to observe the rate law? Why can't it just be a theory where we could just kind of look at our chemical reaction and write the rate law? Well, we explain with the theory, there is a theory that can relate to it, and that theory is the mechanisms, okay? A mechanism is a series of stepwise reactions that shows how the reactants become products. Because when we have our reaction, say we have some generic reaction, we don't know all the steps that are going on in this reaction. This is just what we see at the end. This is what you started with. This is what you ended with. Who knows what steps occurred in between getting from A to B to C? And all of those steps are what is called your mechanism. Okay, so the sequence of events that describes the actual process by which your reactants become products is called a reaction mechanism. Reactions may occur all at once or through several discrete steps. Each of these processes, each of these steps is known as an elementary reaction or elementary process. So if you have it all occur in one step, then you just have an elementary reaction. But if it takes 3 steps, each step is an elementary reaction. So molecularity is really depending on how many molecules you are reacting. So if you are just reacting one molecule, then you basically use the prefix uni. If you have 2 molecules that are reacting, then it's bimolecular. If you have 3, then it would be termolecular. So the molecularity of an elementary reaction tells you how many molecules are involved in that step. Okay, so this means the number of molecules that have to collide at the same time in order for the reaction to occur. Because these 3 molecules have to collide and be aligned correctly and all hit each other at the same time, termolecular steps very rarely happen. Okay, it's just the probability of having 3 molecules all lined up perfectly, all hitting each other at the same exact instant. It's just very rare. So these are rare if they even occur, okay? So if this is in your process, which most likely it will not be, this would be the slowest, okay? Normally, your reactions, your elementary reactions, are going to be uni or bimolecular steps. So nearly all mechanisms use only uni or bimolecular reactions. Because we have multiple steps, all of these steps are not occurring at the same speed. Some steps might be slower than others, some might be faster. So the rate determining step is your slowest step. So if you know the mechanisms by which the reaction proceeds, and you know the speeds of these steps, you can actually determine the rate law from your chemical reactions. So if you look down here, this is an example of traveling on the highway paying a toll. In this first example, toll A is your slowest step, so that is your rate determining step. And in the second example, you notice all the cars are piled up at B, so this would be your rate determining step. So what is required for a mechanism? Okay, your rate law must be able to be devised from the rate determining step. So your rate law, basically what does this mean? Your rate law comes from the slowest step. Because remember, your slowest step is your rate determining step. The stoichiometry of a reaction will actually be obtained when you add up all the steps. Each step must balance, like an equation, and all the intermediates are made and then used up. So they don't appear at the beginning and they don't appear at the end. They occur in the middle and they get used up in the middle. Any catalyst is used and then regenerated. So a catalyst you will see at the beginning and you will see it at the end. So let's do some examples. So here we have this chemical reaction. And it occurs in 2 steps. The first step, they're telling us, is the slow step. So the slow step is your rate determining step. If the first step is your slow step, okay, so the rate law for the reaction is found experimentally to be. So here is what we found experimentally. But they are telling me that the first step is the rate determining step. And it's the slowest step, okay? So let's look at our rate law. In our rate law, we do not have CO. Why is CO not in our rate law that we found? This is experimentally. Well, because CO is not in this is telling me that CO is not in the slowest step. Because remember, your rate law comes from the slowest step. So we have to propose some sort of mechanism. Okay, here is our end reaction. Because our rate law did not match this up, then we knew that there was a couple steps that had to be determined in order to get here. All right, so one of the proposals is, remember, our rate law was this, and it has to be the slow step. So what do we have here? 2 NO2s yielding NO3 plus NO, and this is our slow step. Then the second step is NO3 plus CO yielding NO2 plus CO2. All right, these 2 steps have to add up to equal our reaction. So when we add them up, notice the NO3s go away here, and our NO2s go away, and we are left with NO2 plus CO, NO plus CO2, okay? The NO3 is an intermediate. It is produced and then immediately used up. So intermediates are produced, then immediately used up. And notice in our slow reaction there is no CO, and that is why it's not in the rate law, okay? Remember, the slow step is your rate determining step, and that is the one that you get the rate law from. So if we're plotting our activation energy plots, okay, remember, most of the time we were just seeing one peak, okay? So if you see one peak, you don't form any intermediates, okay? So your intermediates are minimums in the plots, and your transition states are maximums. Transition is when your molecule has enough energy to react. These are very unstable, will disappear immediately. So you cannot isolate these or kind of separate them from the reaction. Your intermediates, they can kind of hang around a little bit, so you can separate them if you want. Your intermediate is not a reactant or a product. You will never see it in the end balanced equation. It is also not a transition state. Remember, it's a minimum energy here. Your intermediates are stable, and in some instances you could isolate them or even identify them. Whereas transition states, they happen so rapidly you can't really stabilize them or isolate them. So let's try an example. So here we have 2-step reaction. Step 1, step 2. And basically 1 when your step 1 is the slow step, which is the rate determining step, it is easy to write the rate law. The rate law is just K times the concentration of the reactants in your slow step. So your reactants in slow step. If I had a coefficient here, that would become an exponent. So write the equation for the overall reaction. So when I add up these two steps, I will get my complete chemical reaction of what's going on. So when I add them up, I have to cancel out elements that are on either sides of the arrows. If they are on the same side of the arrow, you add them together. So here is my complete balanced chemical reaction. Are there any intermediates? Yes. Is something produced and then immediately used up? Produced means it'll be a product, and then immediately used up means it'll be a reactant. So it goes from being a product to a reactant. And in this case, it is O. What is the rate law for the overall reaction? When you have multiple step reactions and your slow step is the first step, the rate law is just K times the concentration of the reactants, in the slow step. So this is your rate law. Okay? So this is the easier example. What happens when your first step is not the slow step? That's a little bit more challenging. So what happens when your initial step is fast? So here we have our overall reaction, and the rate law for this reaction can be found to be this. So here is our overall reaction. When we did experiments in the lab, we found this experimentally. Now, if you look at this, and you just take R equals K times the concentration of your reactants raised to their coefficients, you happen to get the rate law you found experimentally. So you might be tempted to say that this is a one-step process. There are no multiple steps. The problem is, in order for this to be your rate law, that means you have to have a molecule of NO bumping into another molecule of NO, bumping into a molecule of Br. That is 3 molecules. That is a termolecular process, which very rarely happen, if ever. So that means that this reaction is not a one-step reaction. There are multiple steps, and we now need to figure out what those multiple steps are. So here is a proposed mechanism for that reaction, where the first step now is fast. Remember, this is a little trickier now. If the first step is slow, we could write the rate law just using the reactants. But now we have a fast first step. Okay? So step 1 includes the forward and reverse arrows here. Notice this? Why? What do the forwards and reverse arrows mean? This means that your reaction is at equilibrium. And when you are at equilibrium, the rate of the forward reaction is equal to the rate of the reverse. Remember, your overall reaction, and when you want to write the rate law, that depends on the slow step, which is this one here. So what would be the rate law for my slow step? So here I would write the rate is equal to my constant for step 2, that's what this 2 means, times the concentration of NOBr2 times the concentration of NO. Why can't we use this as our rate law? Well, the problem is this guy here, if we add these two up to get my final reaction, what do you notice? This is not in the overall reaction, because this is an intermediate. And the problem is, you can't really measure the concentration of an intermediate. And your starting concentration of your intermediate is 0. So if you put 0 in here, your rate would be 0. Okay, so why can this not be the final rate law? Because of this guy right here, it's an intermediate. Why can't we find the concentration of it? Because we don't have it at the beginning, and it doesn't really stick around long enough to even measure it. The actual rate law, as we showed on the previous slide, was this. So how do we get from here, which is our slow step, to here? What do we have to do? We have to look at our fast step. Now we said our fast step was at equilibrium, which means the rate of the forward is equal to the rate of the reverse. So if I wrote a rate law for this side of the equation and this side of the equation, so here's my forward rate, here is my reverse rate. Okay? And they are equal to each other. This is what equilibrium means. Now I rearrange it and I solve for NOBr2. So I end up with this term is equal to NOBr2. So remember, our rate law from our slow step was this. So now I take this term and I stick it in for NOBr2. So by plugging it in, I get my rate is equal to all of these K's times NOBr2 times NO. All these K's can be combined to just be a generic K. I combine my two NOs to make it NO squared times Br. And lo and behold, this is the rate law that we started with at the beginning. So whenever the first step is not the slowest step, you must use equilibrium here to kind of substitute out the concentration of the intermediate. So now, what if we add a catalyst? A catalyst is something you should be familiar with from bio. Your enzymes here are a type of a catalyst. They speed up a reaction. Speed up reactions. So they increase your rates. And how do they do that? They do that by decreasing the activation energy. Remember, this height here is your activation energy. Notice after you add a catalyst, the peaks of these guys, even though there's two of them, is much less than the peak of the original one. So your catalyst reduces the activation energy, making the hill easier to go over. If the hill is easier to climb over it, you're going to go over it faster. So your reaction will occur faster. There are three types of catalysts. You can have a homogeneous catalyst, a heterogeneous, or enzymes. And these are like the ones that you probably used in bio. So let's talk about homogeneous. Homogeneous means all alike. So if your catalyst is homogeneous, it is in the same phase as your reactants. So if your reactants are all gases, your catalyst will be a gas. So if you look here, everything is aqueous. So this is a homogeneous catalyst. When you have a homogeneous catalyst, it is a little tougher to separate the catalyst out because they are all in the same state. Your heterogeneous will just be in a different phase. So in this case, this is a solid, is your catalyst for these two gases. So the gases pass over the solid, and then they would stick to the surface. When they stick to the surface, that's called adsorption. They're not penetrating into the substrate. They're just sitting on top of it, kind of sticking to it. And then this catalyst will break the hydrogen bonds, allow the hydrogen to move around, bond to the hydrocarbon, and speed up the reaction that way. If I wanted to separate my products from the catalyst, this is easier to do because they're different states. I could easily pull out a solid out of a gas, right? Your enzymes are biological catalysts, and they are pretty amazing, okay? They have a region where your reactant will attach, and that region is called the active site. The reactants are referred to as substrates. So here is your reactant, and here is your catalyst, which is your enzyme. So it'll stick to it like two pieces of a puzzle. Then it will cause it to break apart, and then they will move on. Okay? Sort of like a lock and a key. So in your enzyme substrate model, the substrate fits into the active site of an enzyme like the key fits into a lock. So these are very specific catalysts that work in very specific conditions. So let's see if we can identify in this two-step reaction what is the catalyst and what is the intermediate. So when we have these two steps, we normally add them up to get our final reaction. So let's do that. So here I see that the chlorines will cancel each other out, and the ClOs will cancel each other out. So I end up with this as my overall reaction. Remember, intermediates are produced and then used up. Catalysts are present at the beginning and at the end. So, which one was produced? So, it's got to be one of the ones we canceled out. So, ClO was produced. See, it's on the product side of the arrow. And then it immediately becomes a reactant and gets used up. So, your intermediate in this case is ClO. What was there at the beginning and then there at the end? Chlorine is your catalyst. Notice it was there at the beginning and it is there at the end. It is not used up in the reaction. That is how you determine the difference between the two. So let's try this multiple choice practice problem. Consider the following mechanisms for the reaction represented above. Which of the following statements is true? Step 1 is a unimolecular reaction. Unimolecular means one molecule, but look, there's a 2 here. So I have 2 molecules, so A is not true. Increasing the concentration of NO will decrease the overall rate of reaction. NO is a reactant. Increasing the concentration of a reactant will always increase your rate. So this is false. Raising the temperature will have no effect on the numerical value of the rate constant. Well, the whole last video talked about how the rate constant is highly dependent on temperature. If you increase the temperature, you increase the rate constant. So that is false. The rate law is consistent with the mechanism, and the rate is equal to K NO squared times O2. So that is true. Okay, here's my slow step. If I write the rate law from my slow step, okay, that is not equal to this, correct? But notice, my slow step is the second step. When the slow step is the second step, you have to substitute out the concentration of the intermediate by using the fast reaction. So according to this reaction, the concentration of N2O2 is just going to be equal to K times NO squared. Why is it squared? Because there's a 2 here. So wherever you see N2O2, you're going to plug in and lo and behold, that is our reaction rate. So when you have the slow step as the second step, you have to substitute out the concentration of your intermediate by using your equilibrium reaction. Notice this arrow is going both ways. Okay, and our last example here, you have hydrogen peroxide decomposing. It's represented by the equation shown above. A student monitors this decomposition of 1 liter of the sample at a constant temperature and records the concentration of the peroxide as a function of time. The results are given in the table below. Actually, the table above, right? Which of the following statements is a correct interpretation of the data, regarding how the order of the reaction can be determined? If you have this data, how would you figure out what is the order of the reaction? So A says the reaction must be first order because there's only one reactant. No. Okay, first of all, if you look at it, you have 2 reactants. You have 2 hydrogen peroxides. The reaction is first order if a plot of the log of the concentration of hydrogen peroxide versus time is a straight line. So if you plot this versus time, and you get a straight line, then the reaction is first order. So this one could be true. Let's look at C. The reaction is first order if you make a plot over this versus time. And remember, this is actually second order. So that is not true. The reaction is second order because 2 is the coefficient in front of hydrogen peroxide in the chemical equation. Well, we don't know how many steps were occurring in this reaction. So we can't just write the rate law from this. We don't know the mechanism, right? So B is our correct answer. Okay? And that is the end of chapter 14.